Wall clock versus monotonic clock, the bug hiding in your timing code. Time is a stack, not a number. Here's a stopwatch in 4 lines. It looks right, it passes on your laptop, and one day it reports a negative duration. The bug is which clock now reads. At layer 2, the kernel reads the hardware counter we built at layer 1 and hands your program now. Sounds like one number. But there isn't one now. There are 2, and the whole episode is the difference between them. Both clocks stay on screen from here on. Everything lives on this pair. The first is clock real-time, the wall clock. It's the one that knows it's the 29th of June, 2:30. It answers, "What time is it?" Because it tracks calendar time, it can be reset, nudged forward, or the dangerous case, backward, whenever something corrects it, an NTP fix, or someone setting the date. The wall clock is not guaranteed to only move forward. The second clock is clock monotonic. It is not a calendar at all. It's just a count, ticking upward from some unspecified starting point, usually boot. It can't tell you the date. It can only ever go up. Now correct the clock. Step it, set it, let NTP yank it. The monotonic count does not care. It is immune to corrections, and it never ever runs backwards. Real-time knows the date but can jump. Monotonic can't name the date but never jumps. Back to our stopwatch. It called now, and it got the wall clock. It stamps the start time off clock real-time. So far, fine. But mid-measurement, while the work is still running, NTP decides your wall clock was 3 seconds fast and steps it back. The clock you're timing against just moved into the past underneath you. End minus start. End is now earlier than start because the clock moved back. Your 10 millisecond operation reports as having taken -3 seconds. This is the bug, and on a clock that can also jump forward, the same code can report hours that never happened. The fix is one word. Ask for the monotonic clock instead. Run the identical scenario, same NTP step, same instant, and because monotonic ignores the correction, start and end are still in order. Elapsed, a clean 10 milliseconds. Same code, right clock. Here's the entire rule, and it fits on a sticky note. Measuring how long something took, a duration, a timeout, a benchmark, a rate limit, use monotonic. If you need to know what time it is, a log line, an expiry, a calendar event, use durations, monotonic. Calendar, real time. And the call underneath it all, on POSIX systems, is clock get time. You pass the clock you want as the first argument, clock monotonic here, and it fills a struct with seconds and nanoseconds. The only thing that changes between the 2 clocks is that one ID. One honest caveat so you don't misuse it. A monotonic value on its own is meaningless. It isn't a date, its 0 point is arbitrary, and you can't compare one machine's monotonic clock to another's, or even across a reboot. It is only good for subtracting 2 readings on the same run. That's exactly what a duration is. One question we kept dodging: who keeps correcting your wall clock, and why is it ever allowed to jump instead of easing gently? That corrector is a network protocol called NTP. It lives one more layer up, and it slews when it can and steps when it must. That's the next playlist. Durations don't live on the wall clock. Next, who moves the wall clock and why it ever jumps? Time is a stack, not a number.